Today we are going to talk about the reaction of these two phenol-containing compounds. This is a proton transfer acid-base reaction. So to understand this reaction, we must first label the acid and the base. For this, two red flags can be used to determine which is which. 1. Selenium, a covalent, a nonmetal, is bonded to an ionic metal, lithium. This lets you know that this bond is not covalent. Thus, we know selenium has thus 3 lone pairs of electrons, for it must have a negative charge to ionically bond to the positively charged lithium ion. These 3 lone pairs are apt to act as basic nucleophilic sites that are ready to attack any electrophilic sites. This brings us to the NH2 on this phenol. This nitrogen, which is a very electronegative atom, is bonded to 2 hydrogens. Now, while it does have a lone pair that is apt to act basic, in this case, selenium wins out in basicity, especially since nitrogen is drawing the electrons away from hydrogen, making them more partially positive. Knowing the acids and the bases, we can thus move on to the mechanism. Knowing that this is the acid, we can see that this lone pair on selenium is going to attack the hydrogen, the partially positive hydrogen, which is going to freely release its electrons to nitrogen and be brought over to selenium, yielding the products below. Since this is the acid and this the base, then this must be the conjugate acid and this the conjugate base. Now, when determining strength, we have to use REO. For instance, we see that this NH2 loses an electron, and we must determine how its structure allows it to handle this negative charge that is brought on. With this, we use the A in REO, which is the atom effect. Nitrogen is a very electronegative compound, so it is usually able to handle the negative charge readily. But what we have to understand is that selenium is a much bigger atom. Thus, the negative charge present on it is able to be spread out over a larger volume. And thus, it is actually more apt to handle a negative charge, making it a more stable base and thus a weaker base. With this being a weak base, this nitrogenous base must actually be the strong base. Now, knowing that this is the strong base, we can conclude that this is in fact a weak acid. And knowing that this is a weak base, we can conclude that the selenium hydroxide on this phenol is in fact a strong acid. Now, knowing the relative strength of these acids and bases clues us into the higher pKa values. The stronger an acid is, the lower its pKa value will be. So this should have a lower pKa value of all, while this should have a relatively higher pKa value compared to this compound. However, bases have pKa values as well. And so the strongest base should have the highest pKa value because this is the least acidic of all of these compounds, while the weakest base is just below it. Now, knowing its pKa value, we can predict which products will be in higher concentration at equilibrium. Equilibrium always favors the weakest acids and bases, because we assume that the stronger the acid and the base, the more complete the reaction will be. Thus, we can favor this side, the reactants, at equilibrium. And then we know that these two species will be present in the highest concentration at equilibrium. Now, by understanding lone pairs, electronegativity, and REO, we have determined the mechanism of an acid-base reaction.